We are at Chapter 9, talking about regular structures. There's some good stuff here, and there's some of it that's a little bit dated. Anyway, regular structures, as you might imagine, consist of repetitive structures or arrays of logic. The main advantage offered by a regular structure would be greater ease in managing complex design, greater ease in fabrication because there's lots of duplication of basically this similar entity. And for complex systems, the use of some regular structures typically becomes mandatory. And within a microprocessor, for example, there'd be a variety of regular structures. So there's a large number of regular structures and methodologies. We'll discuss a few of them. We'll look at past transistor arrays, some forms of memory, and so a little bit of programmable logic array, although it's slightly deprecated, as well as some FPGAs, which is interspersed throughout. So often these regular structures are made available from the vendor in terms of a parameterized module or IP. IP again stood for intellectual property. Makes it easier to incorporate into larger ASIC high-level design tools and HDLs if you already have something pre-built for you and you know it's going to work. As opposed to structured logic, though, on the other hand, you could have random logic, and the term random logic is used to describe circuits constructed in much the same way as small-scale ICs would be assembled on a circuit board. So because it's got irregular patterns, it looks disordered or random. Structured logic has some sense of order, regularity, and is often implemented as a type of array structure. So the randomness associated with the logic is somewhat hidden by the overly orderly appearance of the array. So advantage of using a regular structure, there might be some advantage to layout automation, implementation constrained to a regular structure, so some tools may be simplified by placing only one of several predefined cells, so it's slightly more constrained, may or may not make that easier. Another advantage is the use and the reuse of expertly designed and exhausted tested cells. So those would be considered tuned, hardened IP cells or modules. So the first thing we'll look at is past transistor array. They're certainly not a very practical method of implementing ASIC logic functions, but it's worthwhile discussing their construction and some design trade-offs. They're certainly embedded within FPGA core technology, and it does still represent a more structured approach to design. So these can be utilized by programmable interconnect within a specialized IC. So within an FPGA, for example, there would be switch arrays and that programmable interconnect in general. So when the transistor is viewed as a simple switch, it can be used to construct switch arrays, and we'll look at some of the disadvantages of that as well. But the following example illustrates a simple multiplexer that could be constructed. So in this particular case, for example, you'd build a multiplexer such that if A is 1 and B is 1, for example, P1 would be directed to the output. And this could, of course, be simplified a little bit further, and we'll look at that in a minute. So there's a schematic and a truth table for a multiplexer, which is a logic function implemented in a past transistor array. A single transistor NRP type, though, as you know, is not an ideal switch. An NFET, for example, does a poor job passing the high signal due to the threshold voltage drop, and that's made even worse by the body effect. So that's even a higher VT drop because when you're passing a logic 1, there's a body voltage present. The past transistor also provides a delay which would be similar to that of an inverter. So there's some additional problems, issues with the output drive. It's not driven from VDD or ground, but rather from the input. And but there are some alternatives to the past transistor from a transmission gate toward a transmission gate, where you use a transmission gate for the switch. In this particular case, you'd have no VT degradation. You'd still get no voltage drop at all, but at least twice the number of transistors would be required. So here's an improved CMOS design shown below for the multiplexer, and this sort of represents the transmission gate. So it has both an N and a P-type transistor, and sort of blown up here to illustrate that you have to drive, let's say, the N on A and the P on A bar. So at least twice as many transistors, and again, this could be simplified as well. And there'd be other difficulties with respect to implementation, where you wouldn't really implement it in this fashion because you may want to put all the P-type transistors in an N well and all the N-type transistors in a P well, but logically it looked like that. So here's an example of past transistor lookup table selector as per an FPGA. So these are programmable registers here. So when you scan in your data, ones and zeros, this basically is an SRAM shift register. So it's a regular array as well. And you'd put the value of the logic function that you want to be expressed by the selector A and B here. So these would possibly have a 0, 0, 0, 1 here, in which case then if you selected 1 on A and 1 on B, this N-type transistor, or this n-type transistor would be on, and this n-type transistor would be on, and you'd end up selecting this value out. So you basically get an AND gate, and that would be represented there. At this time, take a brief break.